Hi, everyone. Welcome to Lecture 5 of Synchrotron X-rays for Micromechanical Analysis. Today's topics are going to be diffraction from finite-sized crystals or crystallites, and diffraction from a deformed crystal. I'd like to point out we're going to take a microscale or a mesoscale approach. So to start off today, we're going to begin with an equation we've seen before, and we're going to look at the general scattering equation from a body. Plastic scattering. So our total scattering amplitude equal to this expression, where as a reminder, this is the classical electron scattering amplitude. This is the charge density in the object, or the charge density field. Q is our scattering vector. And this delta X is our position in the crystal, or in the object. What we've neglected up to this point is that this term here is actually the general expression for the Fourier transform of the charge density. So Fourier transforms have some nice properties that we're going to use in a sec. For our analysis of finite size crystals, we're going to take one step back and we're going to talk about a simple infinite crystal, what we've talked about in the past, but then we're going to talk about the simple crystal charge density in terms of this Fourier transform expression. So our charge density is going to be a simple infinite sum over all the unit cells. We've got an infinite number of unit cells filling space. And at each lattice point, we've got a Dirac delta function. And this x we've been using as unit cell origins at lattice points. Now, if we plug this charge density and evaluate this Fourier transform, what we actually find for the total scattering amplitude is that it's equal to what we actually get is we get another infinite sum in reciprocals, or in related to the reciprocal lattice this time. So the Fourier transform of the real lattice, the delta functions at real lattice points, is delta functions spaced out at reciprocal lattice points. So with this being the case, we can think about our Ewald sphere construction a little bit differently than we have been. Previously, we were just kind of sitting in reciprocal space, but what we're actually seeing during a diffraction experiment, where we've got a piece of Ewald sphere in different lattice points, reciprocal lattice points spaced out, is that what we're able to see is the Fourier transform of the charge density, which is in contact with Ewald's sphere. So what we're seeing is a little slice of the Fourier transform of the charge density at any given time. So now we're going to move to a finite size crystal, now that we're thinking about these Fourier transforms. So one simple way to describe the charge density of a finite size crystal is to, again, have an infinite sum over all our lattice points. But we're going to multiply it by something called a shape function. And let's not get this confused with shape functions, which are used in finite elements to interpolate between nodal values. This shape function here, all this is a function that's 0 outside the bounds and 1 inside the bounds of an object. So I've got a picture of an example of what a shape function looks like. So here's an example of a shape function and an infinite lattice. So we've got our infinite lattice, and we can think that everything outside the bounds of this shape function is 0, and everything inside the bounds is 1. So those delta functions still exist, and we knock out all the reciprocal lattice points that are outside our shape function. So now what we find, if we evaluate our scattering amplitude now, with our charge density including the infinite lattice and our shape function, and I think I missed before that this V is the volume of the unit cell. Our scattering amplitude A. And so I'm going to write this equation down. I'm going to talk about the pieces in a second. It's more complicated than it looks more complicated than it actually is. Fit. Okay, so we've got these prefactor terms, but what we have here is a convolution. So we talked a little bit on the first class about convolutions, but essentially what this is a tiling operation of, I've got this big S here, big SQ, which is just the Fourier transform of our shape function. Tiled over the reciprocal lattice points. So I've got another picture. And there's the question up on the board one, is the shape function in real space? The shape function is a real space object. Yeah, that's that reciprocal. This SQ here, this Fourier transform of the shape function is in reciprocal space. There's another question too. What is the value of a point if it lies on the shape function? That's a good question. One, you can define how you want, but we'll say if a point lies on the shape function, it's equal to 1. It's just, in a real crystal, we don't have this arbitrary boundary, right? we would draw the shape function so that it includes all atoms that are in the real crystal. So think about it that way. So the shape function is just, we make it so that it surrounds all real lattice points that exist. So the lattice points have to be in the shape function. So now, this convolution operator that I just drew, that complicated integral, all we have to think about is that we have our reciprocal lattice points, and we've got our Fourier transform of our shape function in reciprocal space, and we're going to tile it onto every point. So don't get too worked up about that long integral. It's really just another way of writing this tiling operation. So the big question is, what do these shape functions actually look like? And how do we evaluate them to figure that out? Analytically, the only shape functions that you can solve are for a sphere. And if it is a sphere, the shape function, the Fourier transform of the shape function is a Bessel function. But these days, we can actually solve for these shape functions numerically, and it's actually a pretty straightforward operation using fast Fourier transforms. And so we've actually gotten very, very good at performing Fourier transform operations numerically. So myself, yesterday, I was able to easily generate what shape functions in real space, and then perform the operation of the fast Fourier transform to figure out what the shape function looks like in reciprocal space. So we have here, as an example, is a circle. So the black values correspond to 0, and the 1s is the circle on the inside. And like I said before, I was able to recover numerically the Bessel function. So you see that there's this kind of bright spot in the middle, and then there's these fringes around the outside of the sphere. They're a little hard to see. Now another thing, I've got another example here. I've got a rod in real space, so just it's long in one direction and short in the other. And what we actually get is we get something called flake-like in reciprocal space. So the dimension that's long in real space becomes short in reciprocal space, and you still get these fringes sticking out. But one thing to remember is that big objects or long dimensions in real space become short dimensions in reciprocal space, and the other way around. And another example here is a square, or it would be a cube in 3D. And what you can see is that you actually get these fringes jutting off in reciprocal space that are perpendicular to the faces of the square. So that's something that general, if you have a polygon, is that in reciprocal space, you actually get these streaks, and they've sometimes in papers are referred to star-shaped or asterisms out from the square faces in reciprocal space. And so here's an example too of what happens as an object gets smaller in real space. We can see that the shape function, the Fourier transform of the shape function becomes bigger in reciprocal space. So those shapes get tiled onto every single reciprocal lattice point. And so what's important to remember here is that in real space, as diffracting objects get smaller, the amplitude or intensity distributions in reciprocal space get bigger. So this is the effect that gives rise to something called particle size broadening. As a material becomes increasingly plastically deformed, the crystal breaks. One way to think about it is the crystal breaks into smaller and smaller crystallites that are misoriented from each other. These crystallites become smaller and smaller diffracting units, which then diffract out to larger intensity distributions. So when you hear someone talking about particle size broadening, what they just mean is that the crystal's breaking into smaller diffracting units, and then their intensity that they measure ends up broadening out. And the last point I want to make about these Fourier transforms of these shape functions is that measurement of Fourier transform shape functions is that the core of small angle X-ray scattering techniques. So one way to think about SACS techniques is what users are measuring is they're measuring the Fourier transform of those shape functions around the 0, 0, 0 reciprocal lattice vector, which happens to be the direct beam. So if you understand kind of what you're going after and what you're seeing when you're looking at these Fourier transforms, you can understand SACS techniques. So now we're going to talk about diffraction. From a deformed crystal. And so essentially we have a couple of choices for the diffraction model that we're going to use. And it's the size of what we're going to call a good region of crystal. So if we have billions of atoms, we would use dynamic diffraction. which we haven't discussed in this class up to this point. Billions of atoms. We're going to have kinematic diffraction. With thousands of atoms. We're going to have kinematic diffraction with the particle size effects that we just talked about. What we're going to be using today is kinematic diffraction. And what we're going to do is we're going to build up crystals or grains by building up together lots of smaller diffracting units, which we're going to call crystallites or mosaic blocks. And this is what's known as a mosaic block model. So what we have is each of these colors corresponds to something like a crystal or a grain, and the slight gradations mean that they are slightly misoriented from each other or have slightly different strain states. So what we're going to do is we're going to build up crystals from lots of tiny diffracting units, and we're going to sum together the intensities from all these little crystallites. And again, the crystallites also can be known as a mosaic block. So even though we have billions of atoms, we're not going to use a dynamic diffraction type modeling approach because we're going to break our crystal up into smaller crystallites. And the reason that we can do that is that the actual angular acceptance of a crystal is very small. So it's on the order of arc seconds. So if regions of crystals are more than a couple arc seconds misoriented from each other, they can be treated as separate diffracting units. So in all the analysis that we did previously, when we were talking about our rotating crystal diffraction experiments, we assumed that the crystal that we were looking at, or crystallite, was on the center of rotation. If we're dealing with these real crystals built up from lots of little crystallites, there's no way that all the crystallites can be on the center of rotation. And what happens is the effects of the positions of these crystallites can end up influencing our diffraction data. So what I mean by precession is, so if we're, say, rotating about this E hat 2 direction by an angle omega, let's say omega equals 0, the crystal will be on one side of the origin, and then it can rotate and precess around our rotation axis. So for our analysis of our deformed crystals made up of crystallites, each crystallite is going to have a position P, which is a vector from the origin to the crystallite center of mass. And each crystallite will have its own orientation.
So when you say crystallite, it's that individual block in each grain?
So we're going to have, to try to keep things straight, we're going to have a crystal or a grain that is made up of lots of little crystallites or mosaic blocks. I apologize if I am not clear as I'm going through. But each crystallite has a position P and an orientation. And we've been using crystal to sample as our convention. So what are some of the effects of this change in position? So the first effect that we have is that as a crystal is rotating around the rotation axis, and let's say we have a detector plane here, is that as it's rotating, the distance between the sample and the detector is changing. So effectively, the angles at which diffraction peaks are fixed, but the intercept points with the detector plane are going to change due to this change in distance. The second effect is that as the crystal is rotating, there actually becomes an offset shift. And so in this drawing, the beam is coming down into the page. But we can imagine that even with two crystals, if they were diffracting at the same angle, if they were shifted to the left or right of each other, that they'd intercept the detector plane at different points. So we've got a translation of the diffracted beams and a scaling of the diffracted beams depending on the distance to the detector. And we can calculate how these effects influence the intercept on the detector. So we have a detector plane and a crystal that's a vector P away from the origin. A distance D to the detector. What we want to know, and it's emitting a diffracted beam in a direction K out, hat. What is the intercept point, the C, that we're going to use here? So we can figure that out by solving an equation. So we're going to go back to being careful about what coordinate system we're working in. So we're going to work in the lab frame. And as part of this, the detector plane normal is parallel to the incoming beam. And so this is the simplest case possible, where the detector is detector normal is parallel to the beam, but you can work out more complicated intercepts without too much trouble. But this hopefully will be demonstrative. So if we solve these set of equations, what we find is that our intercept with the detector actually, so this is the case. Sorry. So this first case here, we find that the intercept of the detector so this set of equations here is solving for the intercept of the detector without taking the position into account. This is the first step. But all we have to do to include the position effects make sure this is clear. No.
And C lies in the detector plane, right?
Because C is in the detector plane.
Okay.
Yes.
I think you said that.
Yeah.
It's fine.
But let's get it up on the board.
And that C is just a constant on the left hand side.
Oh, yes. So now including position. We remember that the current position in the plane just ends up being a translational shift of the intercept. And that the position along the beam direction ends up just being a scaling here and added to our distance. So this equation here can be quite informative for understanding where diffracted intensity can show up on the detector and what becomes dominant. So the first case is when the sample to detector distance is very, very small. So in the first case, what we find is that intercept is about equal to just the position terms in the transverse plane. So when we're close, this term becomes dominant. And what we call this, for these experiments, is the near field. So when we're working in the near field, where our diffracted intensity intercepts the detector is dominated by the positions of the crystal during a diffraction event. Then when D is large, the equations revert back to looking like they did when we didn't include position at all. And this is the far field. The important point I want to make is that no matter where you put the detector, there's always going to be some small effects of both. Even if you're in the near field, the direction of the diffracted intensity will show up, but it will be a small influence on where you measure intensity on the detector. And if you're in the far field, you're still going to get small influences from the position of the detector, but the position is going to be mostly dominated by the direction at which diffractive intensity is emitted onto the detector. And I'll have some graphics showing that in a little bit. So now I want to talk about deforming the lattice in a crystallite. And we're going to go back and use some of the continuum mechanics tools that we built in the first class. So in our undeformed state in our lattice, we might have our three crystal basis vectors, and I'll put these knots in here to indicate that these are the initial crystal lattice basis vectors. Got our atoms. As we deform the lattice, our crystal lattice basis vectors might rotate and stretch. And a good way of describing this rotation and stretch of our crystal lattice basis vectors is with a linear mapping or a deformation gradient F. So what we're going to assume is that we can describe the deformation in the lattice in each crystallite with a deformation gradient F. So what does that mean for our lattice points? And more importantly, since we're talking about diffraction, what does deforming the real lattice do to our reciprocal lattice points? So our current lattice positions in the deformed or current state are just equal to the deformation gradient dotted with our the lattice positions in the real or in the reference state. We can see that because so we can see that we deform real, our direct lattice points, but what about our reciprocal lattice points? So what you actually find, if you slope through what the current reciprocal lattice vectors are, and I'll give an example of what the equations look like that you have to work through. So we actually find if you slope through these equations for B1, B2, and B3, you find that the current reciprocal lattice vectors are equal to the inverse transpose of the deformation gradient dotted with the reference reciprocal lattice vectors. And I have the derivation in my notes, which I'll post online. So this is pretty helpful. So now we've talked about what happens when the crystal light's processing around and what happens for the deformed lattice that's different in each crystallite. And just as a reminder, all we have to do now to solve the diffraction, or to figure out when diffraction happens, is to use the same tools we had before that we've been developing. But now we include our deformation gradient into our calculation. So now we've talked about the effects of position, and we've talked about how we can deform the lattice. But the question is, what does that actually look like coming from a deformed crystal? What does our intensity distributions look like? And I have some figures that might be illustrative of what we're looking for, or what we'll see when we build up a deformed crystal from these crystallites. Okay. Oh, I guess I'm gonna have to draw it instead. So what we have what we're gonna have is 3 crystallites here. And they're gonna have a distribution of strain. Since they have a distribution of strain, there are the three reciprocal lattice vectors that are currently diffracting, all have different magnitudes. Because we remember that the magnitude of G is related to the plane spacing. So if these are strained differently, they're going to have different lattice plane spacings. So what happens if we stick the detector in really close? So our case where D is small. What actually happens is the diffracted intensity from the 3 crystallites are going to be dominated by their positions. So we've got the 3 crystallites spaced out, and we're getting intensity from the 3 crystallites on the detector. Now, if we have the detector very far away, what we find is that the diffracted intensity becomes dominated by the angle at which the diffracted intensity is emitted. And what that means is that since each of these have different plane spacings, they're going to be emitting diffracted intensity at different 2 theta values. So they're going to show at different radial positions on the detector. So in the large distance case, the far field, the diffracted intensity from the 3 points are spread out radially, and what this is known as one form of strain broadening. So now we're going to talk about what happens if we have a distribution of orientation. I'm going to keep my pictures here. So again, I have my 3 crystallites here. And now the crystallites are going to be misoriented from one another. And what we remember is that the reciprocal lattice vectors are also parallel to the lattice plane normals. So again, if we're in close, the angle at which diffracted intensity doesn't really matter too much, because we're dominated by those positions of these crystallites in space. So what we find is that we get the same effect between strain and orientation. If we're in close, we're insensitive to both these effects. Now, in the far field, the diffracted intensity will show up in very different positions on the detector. The intensity will show up at a fixed radial position on the detector, but what we're going to get is azimuthal or misorientation broadening. So in summary, position of crystallites has a major effect on where intensity appears in the near field. So misorientation affects the azimuthal positions of intensity. Strain affects the radial positions of intensity. So that's all I have for today. Next week, we're going to have an overview we're going to be talking about stress, and crystal mechanics. So that's it for today. Thanks for listening.